Okay, so if you remember, the last linear transformation video ended with this result. I mean, we saw only the statement. So today we are going to prove it. So this statement links the regularity of a linear operator with the constant term of one of its minimal polynomials. You may remember that although on a finite dimensional vector space any linear operator has a minimal polynomial, but we haven't said anything about that polynomial being unique or not. Okay, right now there is just one minimal polynomial, there may be others, but in any of them the constant term is non-zero if and only if the linear operator is invertible or regular. So let's first prove this. So in the proof we are going to start by considering a minimal polynomial for t. Let although we need not mention that this polynomial is over the underlying field f, but why not? Okay, it just simply tells us that the alpha i's are coming from f. Let this be a minimal polynomial of t, where alpha k is non-zero. Okay, where is this non-zeroness coming from? It comes from the definition of a minimal polynomial, because a minimal polynomial by definition has to be a non-trivial polynomial. So one of the alpha i's at least has to be non-zero. So here, coming from the highest terms, this is the first alpha k, the alpha I, the first alpha I which is non-zero. The other ones which are there after this, they all are zero. Alright, but our aim now is we now focus on this constant term. So this is a two-way statement. Two-way statement means it's an equivalence. So we have to prove two implications. Let alpha naught be non-zero. If this is our hypothesis, we then have to prove that t is regular or invertible. That means t has a left inverse and a right inverse, both of which are equal, of course. I mean, if they exist, they will be equal. Now, because t is a minimal polynomial for t, t is going to satisfy the polynomial. So this will be okay. Okay, fine. Instead of writing I to denote the identity operator, we can also write 1. The thing is that we have to properly interpret this 1, and we should not confuse this 1 with the real number 1. It is the identity operator, which is the function, that function from V into itself that maps every vector onto itself. Okay, just for the sake of clarity, let's write one more term here, alpha 2 t square, and just like that here also let's write one more term than, I mean, the previous one. Okay, so okay, we have started with 0. So this thing is equal to 0. This implies if we keep alpha not 1 on one side and transfer all the other terms on the other side, we then are going to get this. Or from this again we are going to get something else. Now non-zeroness of this scalar alpha naught will be used. And simultaneously, that means you can guess what we are going to do here. We are going to multiply on both sides by the multiplicative inverse of alpha naught, which if you want you can also write as 1 over alpha naught. But keep in mind that this may not be a real number, it's just a field element, where the interpretation of 1 over alpha naught is that it's the multiplicative inverse of alpha naught. Non-zeroness of alpha naught allows us to have that because f is a field. Or 1 is equal to 1 over alpha naught times. Now what we are simultaneously going to do, we are going to take one t outside from this this combination, and so we are going to write that t afterwards. Let us first write what we will be left with: minus alpha k times the k minus 1th power of t minus this times t to the power k minus 2, like that it goes, minus alpha 2 t minus alpha 1 1, okay, because the last one is alpha 1 t, times t. So we have done two things at once. We have multiplied both sides by the multiplicative inverse of alpha naught, and we have also taken t outside. But note that this can also be done by writing t on that side, because it ultimately does not matter. I mean, whether we write this times t or t times this, it does not matter, because you can take t outside on that side also. That is what I am saying here, is that you can write this entire thing as t times Now, if you look carefully, we have been able to express the identity operator 1 as something times t, and that is also equal to t times that something, and that something is nothing but again an operator on phi. So that means this is equal to ts, or let me maintain the order, st equal to ts, where s is this thing. We can write, I mean, now we are going to write S. No, we can write it a little more neatly, where S is minus alpha naught inverse alpha k t to the power k minus 1 minus alpha naught inverse alpha k minus 1 times t to the power k minus 2 and so on alpha 2 t alpha 1 1, and this S of course is an element in our algebra. So that just proves that T is invertible. Now we have to prove the converse. Conversely, let T be invertible, and the minimal polynomial is already there. Okay, we started with the minimal polynomial, it is there regardless of which implication we are trying to prove. But now our hypothesis is that T is invertible or regular. We want to prove that alpha 0 is not equal to 0. But suppose that is not the case. Suppose that in spite of T being invertible, alpha 0 is 0. Then we again write the equation, that is the fact that T satisfies its own minimal polynomial. But this time, keeping in mind that alpha 0 is 0, and that gives us alpha 1 T plus alpha 2 T squared, and like that. Since T inverse exists in A of V. That's what being invertible means. T inverse is that operator by which if you multiply T either from the left side or from the right side, you are going to get the identity operator 1. It exists. That's what T being invertible means. So what we can do is that we can multiply on both sides of this equation by T inverse and get this. Alpha 1 1 plus alpha 2 T, and like that it goes. Now something will go wrong because of this equation, or something has gone wrong already. We need to understand what that thing is. Okay. Now already alpha k is non-zero. Do you remember that is the case even before starting the proof? Right after writing a minimal polynomial for t, we declared that alpha k is non-zero. Now you may of course ask, what if alpha k is equal to alpha 0? No, that cannot be. That's because a minimal polynomial by definition has to be non-trivial. So if we are assuming that alpha 0 is 0, then something else must be non-zero. Okay, otherwise it's the trivial polynomial, that is the zero polynomial. So one of these things has to be non-zero, I mean one of the surviving coefficients other than this one, and alpha k is non-zero, and alpha k in particular because of this fact is not equal to alpha 0. But that means what? Then what do we see from this last equation? We see that t is now satisfying another polynomial, but then t satisfies the non-trivial polynomial let's write what that polynomial is. Alpha 1 plus alpha 2x plus alpha k minus 1 times x to the power k minus 2 plus alpha k x to the power k minus 1 in fx which has degree k minus 1, and the fact that this degree is exactly k minus 1 comes from our assumption that alpha k is non-zero. But because of that same fact that alpha k is non-zero, that minimal polynomial has degree k. However, here we have got a non-trivial polynomial of smaller degree than the degree of the minimal polynomial, which also t satisfied, but that cannot be because that contradicts minimality of p. But this contradicts the minimality of p, or more specifically the minimality of the degree of p. There may be some other choices for p, some other polynomial. However, that k should not, you should not be able to reduce the value of k, because then that degree should be minimum. But that is not happening here, and this has happened because our careless supposition that alpha naught has to be equal to 0. So our supposition is wrong, i.e. alpha naught has to be non-zero. So this is the other half, the other implication. So now we have established the fact that no matter what the minimal polynomial is for the given operator, non-zeroness of its constant term is equivalent to regularity of the linear operator. If one of them is true, then so is the other. And now we are going to see some very nice corollaries of this result. You can understand that since regularity has been reduced to a constant being or not being, not being 0, so it will have consequences. So we are now going to see those consequences. So let us see the first corollary will be almost immediate. We do not have to do anything to prove it. Okay. And to show why that is the case, I am going to keep this for some time, this S. So this is corollary 1. If V is finite dimensional over F, then we need to, okay, what is T? We need to say that first. Then the inverse of any invertible element in the algebra AB is a polynomial expression in T over F. So what we are saying that if V is finite dimensional, of course, that's what we are talking about here, over the field F, and T is an invertible linear operator on V, then its inverse exists. Being invertible means there is an inverse, and this inverse itself is a polynomial expression in T over F. And we just see that here. When T was invertible, and that is, you see, by what we have proved here in the theorem just now, that happens precisely when that constant term is non-zero, and we have found this expression for the inverse. Looking at this expression, you can clearly see that the expression itself is a polynomial expression in T. Okay, and that is the claim in this correlation. There is in fact nothing to prove here. It's just simply an observation that is coming out of the proof of the previous theorem. But there are other corollaries too. So let's see them now. This one is nice, but it's really not that surprising, given that we have seen how that proof works for the theorem. But let's see the other corollaries now. If V is finite dimensional over F, then a linear operator on V is singular. So this time we are not talking about regularity, we are talking about singular operators, the operators which are not invertible. If and only if there exists a non-zero element, a non-zero operator S in A of V such that St equal to Ts is equal to 0. S is non-zero, but the products St and Ts are 0. Such an S exists if T is singular and if such an S exists, then T is singular. So it's also both ways. So let's see the proof. Let T have a minimal polynomial. There will be a minimal polynomial because the space in question, the vector space, is finite dimensional. Let T have this minimal polynomial. Okay, now since T is singular, this alpha naught will be 0 by our theorem. Since T is singular, we have this, and T is also going to satisfy this polynomial. Now, so that gives us what? 0 is equal to P of T, but with alpha naught 0, we have this alpha 1 T plus, let me write one more term, alpha 2 T square, and so on. Okay, well, if you want, you can write here that alpha k is non-zero. I forgot to write it. Okay, you please write that T has minimal polynomial this where alpha k is non-zero. Alright, now you can see that from this expression, this polynomial expression, we can take T outside as a common term, and that too we can write it in two different ways. I mean, depending on which one you write first. You can write it like this: alpha 1 1 plus alpha 2 T and you can also write T afterwards. Okay, and this implies 0 is equal to St is equal to, I should have written this first, Ts is equal to St, where you know what S is. Where S is this. It looks like we have almost got our S. However, we must now make sure that S is non-zero. Okay, that condition is there, because otherwise there is nothing surprising about it. No, if S is 0, then of course it is 0, but S is non-zero. Now, is S really non-zero? Let's see. There should be some reason for that. No? Since this polynomial which now we can see is what you use in order to get S. I mean, in this polynomial, if you replace x with t, that gives you S. That is what S is. Since this polynomial, there is one more term in fx has degree k minus 1 and is non-trivial. These things look a little confusing if we do not write this extra condition that alpha k is non-zero. That non-zeroness makes the degree of this minimal polynomial k, and that non-zeroness also makes the degree of this polynomial k minus 1, and it also additionally says that it's non-trivial. In fact, that's why it has a degree. So, minimality of p then forces this expression to be non-zero, because otherwise t would satisfy this lower degree polynomial, but that is not possible due to p being the lowest degree non-trivial polynomial which t will satisfy. Okay, there can be, again I am saying, multiple such choices for p, but not I mean, you cannot lower the degree. The minimum possible degree is k. So because of these things, S is not equal to 0, and that's what we needed, right? So we have been able to find such an S, but this is only one half. We have found such an S. Now we have to prove the converse also. Conversely, suppose St equal to Ts is equal to 0. Now this S is not that S, okay. This is converse. This part is independent of what we did before this. For some non-zero S in A of V. Our claim is that T is singular, but suppose that T is not singular. Singularity itself means lack of regularity. So if we are saying something is not singular, then that just simply means that it is regular. Suppose T is not singular, then T is regular, i.e. T inverse in A of V exists, but then note that S can be written as S times 1, of course. We can write it like this because 1 is the unit element in the ring A of V. However, 1 itself can be written as T inverse. Our supposition that T is not singular has led to the existence of T inverse, which is why we can write 1 like this. And then you use the fact that we are in an associative ring. However, ST is 0. This is equal to 0, and this directly contradicts this condition. This condition. S is not equal to 0. This is a contradiction. So that means this supposition is wrong. So T must be singular. And now only the proof is finally over, proof of this corollary. And there is another corollary also. This is the third one. What does this say? Oh, so this is another somewhat surprising fact, that in order to have a linear operator T invertible, it's enough to have it right invertible. Just that itself will imply that it is invertible. Right invertibility automatically implies left invertibility, but keep in mind that that condition is always there in the background, that the space on which we have the linear operator is finite dimensional. If V is finite dimensional, over F, then T belonging to A of V is invertible if it is right invertible. If it is right invertible. Now, how to substantiate this claim? Oh, it is not really that difficult. Proof. Because T is right invertible, so there is a right inverse Tu is equal to the identity operator for some u in A of V. Okay. Now our aim is to prove that T is invertible. Suppose that that is not the case. Suppose that T is not invertible, then that means T is singular. So by corollary 2, St is equal to Ts is equal to 1 for some non-zero s in A of V. However, now something will go wrong when we combine this with this. Oh, okay. This is not 1, this is 0. Now, S is equal to, in fact, you may already have guessed that now we will be able to show that S is in fact 0. So in place of S, what we can write, okay, yes, S1 itself will work, S1, and in place of 1 now we are going to write TU using associative law. This becomes ST times U. However, ST is 0, so we get 0. This is a contradiction. So that means our supposition is wrong, that T is not invertible, so T has to be invertible. Therefore, T must be invertible. So these are the three corollaries which immediately come out as consequences of that theorem. Alright, now after this, the author says that, okay, fine, we have said some things about regularity or singularity of a linear operator in terms of some things, say in terms of its minimal polynomial, that is whether its constant term is or is not 0, and then there are these consequences. However, we are still we haven't said anything about what happens when such a regular or singular operator is applied on a vector V. Okay, that we haven't seen. We haven't seen the action of T on the objects that are there in the vector space on which T is an operator. So this next theorem is about that. So this is also a necessary and sufficient condition for an operator to be singular, but now in terms of a vector from the space on which it's an operator. If V is finite dimensional over F, then T in A of V is singular if and only if the T image of some vector V is equal to 0 for some non-zero vector. That's the thing. On the zero vector, if you apply any operator, you are going to get 0. That is a basic property of operators. But this is non-zero in V. Let's now prove this. And in proving this, in one half of the proof, we are going to use the fact that there is such an S which is non-zero, but ST and TS are both zero. That thing we are going to use. And that of course will be used in that part where T is assumed to be singular, so that such an S exists, and then we will look for this V. But the other half is a little different. Let T be singular, then by, or it was the second one, right? Yes. Corollary to ST is equal to TS is equal to 0 for some non-zero S in A of V. Okay, now let us concentrate on this fact. S is a non-zero operator. What does that mean? It means that it's not the zero operator. What does the zero operator do? It maps every vector in V onto the zero vector in V. So S being non-zero means that there is at least one vector in V which is not sent to the zero vector by S. Since S is non-zero, there exists a vector U in V such that US is not equal to 0. US is a vector again in V, but it's not 0. And this demonstrates the non-zeroness of S. Now, and this US is in fact going to be our V. With V equal to US not equal to 0, we have Vt equal to US T, but that is just U times ST. ST, however, is the zero operator. So it's going to now send U to 0. So you see that in spite of V being non-zero, Vt is 0, and that's what we were seeking. Conversely, let there be some V not equal to 0 in V such that Vt is equal to 0. Our aim now is to prove that T is singular. So let's assume the contrary. Suppose T is regular, then T inverse in A of V exists, but that is going to give us what? Did you see something here? What we have done is that we have applied the operator T inverse. See, T inverse is also a linear operator on V. We have applied this operator on the vector Vt. which actually is nothing but the 0 vector. Now, because T inverse is a linear operator, the image of 0 under this operator is again 0. Okay. However, this thing is V. And this contradicts this condition. But this is a contradiction. So that means our supposition is wrong. What was the supposition? That T is regular. Hence, T must be singular. In other words, a singular operator must send at least one non-zero vector onto the 0 vector. If there is no such non-zero vector, then it must be regular. And if you think if you recall what the kernel of a linear operator is, this entire thing says that a linear operator is singular if and only if its kernel is a non-zero subspace of V, because the kernel is now going to contain this non-zero vector. Alright, so these are the things. But now, before we stop the video for tonight, let us just see one. It's not really anything new, but it is there. Something called the range of a linear operator. And we will end the video with one result which tells us again another condition for an operator to be regular, but in terms of this range, you can say so. So the definition is just simply this. And note carefully that although the results, all of them almost, are about finite dimensional vector spaces, but the definitions are being made for any vector space. That's because the infinite dimensional versions of, I won't say these results, but similar things are there in functional analysis in some other form. I mean, at least the notions are there. The results may not be there. Okay, so now the definition. Let T be an element in A of V where V is a vector space over F, may be or may not be finite dimensional. We don't know. The range of T is the subset this subset of V. So you can see that this is simply the range of the function T. Okay, if okay, let's just go back to the things that we have in a function. I mean, a little terminology. The first set that you see here in any function is invariably called the domain of the function, but the second set has different names. Okay, some people call this the codomain of T. Now you know that the outputs for the function T may not form the entire V, but may only be a subset of V, may be a proper subset of V. That thing is called the range of T by these people who call this second set codomain. However, somewhat annoyingly, some other people call this second set itself the range of T, and the range that you see here for these people by the other people will be called the image set of V under T. So here by range we mean this, that is the set of output vectors. In fact, we can see that here in this definition. Now it turns out that this subset is not simply a subset but actually a subspace of V, and it's very easy to prove. I leave the proof to you. You just have to first of all make sure that this Vt is a non-empty subset of V, because here the same set V, okay, and then you apply the condition for a subset to be a subspace, that is the sum of two vectors from here needs to again be a vector in this, and if you multiply a vector by a scalar from this set, then it is again a vector in that set. Okay, that part I leave to you. So prove that Vt is a subspace of V. Now you can understand that. Let me just see some, let me just tell you about some things which are going to come next. If V is finite dimensional, then this being a subspace of V is also finite dimensional, and the dimension of this range is what we call the rank of the linear operator T. That same thing that you have for matrices, rank of a matrix, like that the rank of a linear operator is by definition the dimension of its range. Okay, so those things will come. And now finally let us see one result about again regularity of an operator, but now in terms of range. And for this result we are not going to see the proof now, but in the next video. So here's the thing. Yeah, it is 614. The statement itself won't mention the word range, but it's about range. If almost all of these results start by mentioning that V is finite dimensional. If V is it's a little cumbersome to keep writing finite dimensional. In some textbooks they adopt f.d. You can do that, okay. You just have to say it once and then you keep doing it. If V is an FD, finite dimensional over FD vector space over F, then T in A of V is regular in if and only if T is onto. In other words, T as a function from V to V is an onto function, a surjective function. That is one condition, and being regular is the other condition. If V is finite dimensional, then these two are equivalent to each other. So you can see that there is no mention of range. However, T being onto is nothing but Vt being equal to V. In other words, the range being equal to the codomain. That's what ontoness is, right? So we will prove this in the next video. So that's just it for tonight. Our next upload is this coming Saturday, and on Saturday we are going to see calculus. Now because we have completed the theory part of that section that we went through recently, this Saturday we are going to see exercise problems. In fact, I think we have already started solving exercises. So we will just see more on those exercises where we have those complicated graphs, complicated looking wavy sine graphs. So that's it, folks, for tonight. So see you on Saturday. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.